Okay, so I guess we should start. Any questions at this point of this about the stuff that we went through last time? Okay, then let me pick up where we were. I want to re-explain the thing that we were talking about. Let's see, where were we? We were on, back to chapter 2 here, array lists. And we were talking about the remove method here. Namely, the order n is a worst case number, and the best case is order 1. And I'll just have a little thing here that we can do. So if we're removing the last item in this array list, there's really not a heck of a lot to do. All we have to do is adjust the size of the array list, and then the last element goes away. So that's order 1. However, if we're going to remove the first item in the array list, that means that everybody else has to move down 1 position, and then we can get rid of the last one and readjust the size. So that's why that's an order n. So in general, in the long run, if you're doing a lot of operations, we're going to say it's order n. Sometimes you're going to be removing the first one, which is the most expensive. Sometimes you're going to get rid of the last item, which is the easiest one. But overall, it's going to average out. You're going to have to move about 1/2 of the items. And since there's no order n over 2, remember we get rid of the constant, it's order n for removal. Now the question is also, because some people ask me as well, how did you find this out? And the answer is here in the documentation. It tells, let's make this a little bit larger here. For example, all of these operations run in constant time. The add operation runs in what's called amortized constant time, which means that if you add n elements, it requires order n time. We'll talk about this amortized business a little bit later on. I don't want to get off track and give you a deep discussion of it. Just to say it's order n when you're adding n items. And then all the other items are in roughly linear time. So this is one way you can find it out. The other way you can find out what it is you can actually download the source code and you can look at it and see how they wrote it. That's the hard way. If somebody documents it, that's the best way. And then here, for example, for a hash map, it says this implementation provides constant time performance for get and put. And then it talks about a lot of other stuff called initial capacity and load factor. And we're not going to talk about those now, but we will find out about them when we discuss hash maps later on in the course. I don't remember which chapter it is, but we'll talk about that when that happens. And that is how I knew that for a hash map, okay, when you copy something to another hash map, that's order n. Okay, and also iterating through it is order n. It's linear. But everything else, when you get an item, when you put, which sets the value of an item, removing and asking if something is in the hash map or not, those are all constant time. So hash maps are really, really efficient. Let's go back to the array lists, by the way. And remember, I was saying that the removing an item is really efficient at the end and really lousy at the beginning. So our question is, can we test this? And that is what this program does. So let's go and look at this business that we're going to do another one of these timing examples. So here I'm going to time remove. I'm going to have a length of my array list and a true or false, whether I want to remove the first, or false means don't remove the first, remove the last. And I'm going to have 25 trials and ignore the first 20, because again, the JVM needs time to get stabilized. And then here I'm going to create a new array list, and then I will add to it so that I get the number of items that you requested. Then I'm calling this. This is something new that I talked about it briefly, system.gc. That's the garbage collector. Because there could be a lot of objects that get created while I'm doing this loop, and I don't want them to be around in memory when I start my test. Then I get my time, and then I go through 1,000 iterations of removing the first one. Or if I say I didn't want to remove the first one, I remove the last item. And I always have to recalculate list.size minus 1 every time through the loop, because when I remove something with 1,000 elements, now I only have 999 left the next time I go through the loop, right? And then if this is one of the ones I want to keep, I add its time on, and then I return the average. Then what I'll do is I'll time the removal for the first on a 2 million item array list, and then a 1 million item array list, and then 100,000 items. Let's run this. Now the 2 million items takes a long time, because it has to initialize an array list that has 2 million things in it. And notice there's a gigantic difference between removing the first and removing the last. For 1 million items, the timing for removing the last item is about the same, and for 100,000 items, it doesn't make any difference. Whereas the difference between 100,000, 1 million, and 2 million for removing the first item, there's a big difference in terms of how long those take. And if we were to graph them, we would see that it's a linear graph. So everybody okay with this idea that we can test things using the timer? The timer is not going to tell us whether something is linear. It's not going to analyze the algorithm for us. All it's going to do is it's going to execute the algorithm, and then we look at the times and say, oh, wow, that looks linear, or, ooh, that's exponential, or whatever. Yeah, question?
How do you make them so calculate the by?
Oh, this was here. I said there are 25 times I want to go through this loop. That's this here. And I want to ignore the first 20 of them. So after I'm done with a trial, I say, if my trial number is greater than or equal to 20, that's one I want to keep. And I'm going to add that total to add the time that it took to the total time. That's one way to do it. Now, since we're going to be doing, you might want to be doing a lot of timing. There's a lot of stuff that we have to duplicate, like this loop here and the garbage collection, and then this, and then doing the test to see if you want to keep it or not. Gee, wouldn't it be nice if we could avoid having to duplicate that every time we write a test? And I put this video up for this last time. Leah, I think it was Monday afternoon. I don't know, did any of y'all see that in the announcement? Okay, if you didn't have time to look at it, it doesn't matter. I'm going to be going over it now. And in fact, I've written an improvement to it already. So what I'm going to do is I'm going to make a framework that allows us to do the testing and gets rid of all the duplicated code so we don't have to write the stuff that's the same every single time. So this time I'm going to have the number of trials you want to run and the number that you want to keep, not the number to ignore, but how many you want to keep at the end. So it's only going to be the reverse test. And by default, I'm going to say run each test 25 times and keep the last 5 items, or last 5 times. You can change that if you want to with this constructor, where you tell how many trials and how many you want to keep, or you can get and set them with the getters and setters. So there's nothing new with these getters and setters, but it just gives you control over each of those parameters. Everybody okay with that? Now, what